Okay, so I guess everyone remember whatever we have studied in last class. I'm hoping that all of you remember the basic principle behind PN junction, how PN junction works, right? Tell me. And how many of you solved the problem of 25.2, sorry, 25.1? Tell me guys, how many of you solved the problems of 25.1? Were you able to solve the problems? Were you getting the concepts? Tell me. Tell me guys, have you solved the problems? Harsha, Harshita, Kritika? Guys, am I audible? Yes, point one, point one. I'm asking about point one only, not point two. Okay? Okay, very good. So today we are going to start the next topic, which is transistors. Okay. Now, before starting this, just let me ask you one question, right? What we already know about transistors. Now, if I talk about our daily life, can you imagine our daily life without transistors now? Tell me, can we imagine our daily life, right, without transistors? No, right? Because whatever we see, whatever we use, right, whatever electronic we use, it is made up of transistors. Yes, tell me. Be it computer, be it your phone, be it your microphone, be it your earphone, everything is made up of transistors, right? Now, it is surprising that how can like when I was a kid, I used to think, right, how my electrical signals is getting converted into my audio signals, okay, or how I'm talking about, like when I speak in mic, right, I can hear the loud voice from the speaker, okay, like how uh, this buffers or speaker works. So I used to think like that, right, how these things works. Now, when you think about it, okay, so I hope all of you have seen that mic as well as speakers, right? Okay. Now, when we speak, what do you think? What happens? Just think about it. What do you think? What happens? I'm not talking about any technicality, right? I'm just talking about your intuitive thought. Suppose you speak in a microphone. Just imagine that big microphone, okay, which was like a handhold microphone. Yeah. So my question is how that audio is converted into electrical signals. What happens? Have any one of you broken down any speaker? Tell me. Anyone? Yes. So, right, magnet hota hai. Yes. Very good. So whenever you break down a speaker, okay, you see a diaphragm kind of thing attached with a magnet, right? And this diaphragm kind of thing is having some coils, right? ये तो सबने देखा होगा जिसने इसने तोड़ा होगा. Think about it. Yes or no? And almost the same thing happens in mic. Okay. Now, so I can say that, okay, there is some electromagnetic conversion, right? There's some electromagnetic conversion due to vibration of this diaphragm. Okay, due to vibration of this diaphragm, right? When you talk about woofer or any speaker, they vibrate, the diaphragm vibrate. So it works in the same way as our ear works, right? Because when we talk about hearing or when we talk about any audio signals, it's just the vibration, right, everyone? Right? Now my problem is, okay, those vibrations are very small vibrations, okay. It cannot create that much electrical signal so that we can hear that loud voice in a speaker, right? Because when you speak in a mic, okay, even though because of whatever you speak, there might be some vibrations in the speaker, but that is not enough, right? That vibration is not strong enough to create that much of electrical impulse or electrical signal, right? Same as what is being produced by your speakers, yes or no? Tell me, yes or no, right? So how that happens? Okay, that's my first question. Second, we talk about calculators, we talk about phone and laptops, right? Whatever we use, we put a like we put any input and we get some output, right? Suppose I want to use a calculator, right? Or I want to use my phone. So whatever we want to do with laptops, calculators, we get some output, right? By giving some input, we get some output. Now, have you ever thought how does that happens actually? Tell me, how did that happens? Okay, most of you, yes. So most of you, when you talk about languages, most of you know about computer languages, yes or no, right? Yes. Okay, now before computer languages, when the computer languages was not discovered, okay, there's something called assembly language. Sorry, assembly language. Okay, now what do you mean by assembly language? So when you talk about logic gates, I hope all of you have studied logic gates, right? How logic gates are the basic building block for any command that we put in our computers or laptops, right? Or calculator, right? And we know that when we talk about any language, it is composed of this 0 and 1 binary digit, binary codes, right? Now, have you ever thought that how these binary codes are generated? Think about it. Have you ever thought that how these binary codes are generated? And what is this binary codes? Tell me, have you ever thought? Yes, very good, Harsha. So basically, these are generated by the, yes, voltages, right? Changing voltage, okay, right? Got it. When there is no voltage, it is considered as zero. And there is some voltage, right? Some voltage, it is considered as one, right? Got it? Tell me, right? So I can say that, okay, if it's that simple, right? If it is zero, right? Or if it is something, then we have zero and one. So I can say that, okay, something is working like a switch, right? Okay, on, off, on, off. Yes or no? Tell me, yes or no? So whatever we use is based on the switch, right? On off, which is producing these signals, 0, 1, which in turns producing these binary numbers, which in turns producing your assembly language, which in turns producing, right, your more complex commands that we use as your computer languages, right? Okay, right? Okay. Now, I hope all of you watched the video that I have sent, right? If you would have watched, right, why I just sent the video, because it was 5 minutes video, it would have created the curiosity what happens. Okay, so see, I'll just tell you in front, right? This topic is very deep. Okay, very means very deep. So obviously we won't be discussing each and everything, right? Because when you talk about a branch of electrical and electronics, or electronics and communication, right? Electronics and communication. It is totally based on this topic. Everything is based on this topic. Okay, right? Got it? Okay. So let's start this topic and let's see what are the topics that we are going to study today. Okay. So when we talk about topics, right? So there are many type of transistors. First of all, there are many type of transistors. Okay. There are MOSFETs, there are BJTs, right? There are different type of transistors, but the transistors that we will be studying is a very basic type. Okay, they are known as BJTs, right? Bipolar junction transistor. Okay, bipolar junction transistor, right? Why it is called as bipolar junction transistor, we will study that. Okay, so the topics that we will be covering would be first, the construction and working of bipolar junction transistor. Then, what are the different configurations of BJT? We'll be studying about only one configuration, right? Then the different parameters associated with BJT, which is your current and voltages. Okay, then input and output characteristics. Now, this is very interesting, right? This is very interesting. This is quite intuitive. Now, first of all, let's think about your mic. Just think about your mic and speaker, right? So mic and speaker are kind of a setup. What do you think? What would be the input for that setup? Tell me, what do you think? What would be the input for your mic and speaker setup? Yes, very good. So when you speak, right, it creates a small, yes, a small electrical signals, right? Yes or no, right? When we speak, it creates a small electrical signal. That should be your input. Yes or no? That should be your input, right? And when we talk about output, right? When we talk about output, then that small signal, right? Okay, that small signal is basically converted by somehow amplified, right? It is amplified, yes, okay, into much larger signal, which again converted into vibrations, right, which converted into sound. Yes, okay, so we will discuss how this input and output signal are formed. Okay, then different states of BJTs, right? And when we talk about the applications, so we studied the two applications. I just discussed the two applications, first as amplifier, second as switch. So we will discuss both of the applications, and then we will discuss logic gates. Okay, right, everyone? Right? Okay. So let's start with constructions and working of bipolar junction transistor. Okay. Now, when we talk about construction, okay, bipolar junction, what do you mean by bipolar junction? Tell me. Tell me. Means we have already studied PN junction. Yes or no? We have already studied PN junction, right? So I hope all of you know what is PN. That's why I asked that you should know, you should revise what we have studied last class, right? Now suppose, forget about this section. Forget about this section for now. Okay, suppose we have N type over here and P type over here. I'm just asking you to forget this for now. Okay, right? This is N type, this is P type. What do you think? What will happen? No biasing. For now, I'm not giving any biasing, right? So because this is NP, right, there'll be a junction development over here. Yes or no? Yes or no? Tell me, right? Okay, this is your first junction. This is your first junction. Yes, and this will be your first depletion region. Agree, right? Okay, now forget about this one. This is also a N-type. This is also a N-type, because obviously if it's P-type, then it doesn't matter having two different junctions. Okay, it is also N-type. Now this is also becoming a PN junction. Yes or no? This also becoming a PN junction, right? So we have one another junction over here. One another junction over here. Okay, so this is your second junction, right? Got it? And it will behave normally as your PN junction without biasing. So there's nothing new in that. Okay, right? Got it? So this is the construction, right? So what we do, we just have two junctions. Okay, when we talk about diodes, normal diodes, we just had one N and one P semiconductors, which is joined together, or basically which is made in such a way that it will create one junction. Okay, got it? Okay, now let's do some biasing, right? So I hope all of you understood this, what we are doing. I'm just taking from the very scratch, step by step. So we have two junction over here. Basically, there are two depletion regions. It is your N, this is your P. and this is your N. Okay, right? Now, let us suppose I give some voltage over here, right? Let us suppose I give some voltage over here, right? Some voltage, okay, some positive voltage over here, right? And this is, suppose it is connected to earth or zero potential, right? You can call it as triode, but it is not called as triode, it is called as transistor, BJT. Okay, right? Now think about it. What will happen? I'm just talking about this NP junction, right? I'm just talking about this NP junction. Tell me, is this forward biased or reverse biased? Think about it. Forward biased or reverse biased? I'm giving some positive charge, right? Some positive charge, and this is very less. I'm just giving like 0.7 for now. Okay, just 0.7, not more than that, right? Very small potential. Okay, still it is forward biased and reverse biased. Forward biased, very good everyone. Okay, now here I gave suppose 5 volt plus 5 volt. Now what do you think? This PN junction is reverse biased or forward biased? This junction, this is junction 1, right? So it is forward biased, right? Forward biased. What about this junction? Okay, this junction is reverse biased, right? Okay, anyone have any issue? Anyone have any issue in this? Tell me, yes or no? Step by step, right? Step by step. Okay, now let us see what will happen. So this is your N type, means we have lots of electrons, lots of electrons. This is also N type, electrons. Now, in order to have, right, this construction to behave as bipolar junction transistor, we should have some conditions. Yes or no? Tell me. We should have some conditions, right? Otherwise, if we see just this structure, right? So we have holes over here. So I'll just write it as P. Okay, P. Because if we see this structure, so I can say that, okay, this is forward bias. So electron will move from here to here, right? Then it will recombine. That's it, right? That's it. Nothing else will happen because this is reverse biased. Electron cannot come from N side to P side. Okay, so what's the work of this transistor, right? So there must be condition for this to work. Yes or no, guys? Think about it. Yes? Now, what do you think? What can be the condition? Just think about it, right? Intuitively, what should be the condition? Think about it. Okay, I'll give you one simple problem. I'll give you, no, if you increase the voltage, still it will move in this direction, huh? Right? All the electrons will go here, right? Yes or no? Now think about it. Think about a scenario. Okay, think about a scenario in which suppose you have 50 chairs. Suppose you have 50 chairs. Okay, right? And in a classroom, suppose you have 50 chairs and 40 students, right? Case 1, what will happen? All the students will take up this chair. Yes or no? All the students will take up this chair, right? But what if I'm having only 10 chairs? I'm having only 10 chairs and 40 students. Tell me, what will happen in this case? And again, there's this different room, right? There's this different room, right? So I can sit, only 10 can sit now, only 10 can sit. What about these 30 people? What about these 30 people? They will move to next classroom, yes or no? Or they'll be pushed into next classroom, right? Even though they want to go or not, doesn't matter, right? But there's not enough chair, right? So they will be pushed into next classroom. Yes, agree, right? Okay. So how can I relate this with my condition? Now let's suppose we know that whatever happens in this junction depends on doping. Yes or no? Depends on doping, right? Now suppose this N junction, suppose this, wait, Yeah, this n-type semiconductor is highly doped. Suppose this is highly doped. Okay, highly doped. Highly doped. And this is very lightly doped. Very lightly doped. Right? Okay. So if it's very lightly doped and it is very thin also, what do you think? What will happen? Think about it. What will happen? Intuitively think, what will happen? Tell me, guys. Right? So electron, this first of all, this depletion region will be very small, yes or no? This depletion region will be very small, right? Okay, electrons will move, more electrons will move from n-type to p-type, more electrons will move from n-type to p-type, right? But since it is very lightly doped, very few electrons will replace the holes, okay? And most of the electrons will be pushed, right? Wait, I'll just change the color, okay? And most of the electrons, so some electrons are moving from p-type to, sorry, n-type to p-type, right? Okay, but most of the electrons will be pushed, yes or no? Sorry, guys. Okay, so most of the electrons will be pushed into n-type, even though it is reverse biased. Even though it is reverse biased, right? Most of electron will be pushed in n-type. Yes or no? Tell me, guys. Yes or no? Right? Okay. Now, this is positive charge. This is positive charge. There's one more reason, because this positive charge, and this is your, again, this is at higher potential as compared to this p junction. That's why it is reverse biased. Okay, right? Okay. Now, because of this, the electric field is in this direction. Yes or no? Right? Because the major issue, what was the major issue? The major issue was crossing this depletion region. Yes or no? Once it crossed the depletion region, electron will move toward this side. Yes or no? Tell me. Once the electron cross this depletion region, okay, they will move toward this side. Okay, agree? Yes or no? Think about it, right? So are you getting the idea what happens inside this structure or this construction? So even though the second junction is reverse biased, electron is moving from this p-type to n-type, because this p-type is very lightly doped and it cannot accommodate all the electrons, right? And the electrons will be pushed into n-type. Yes or no? Yes or no? Okay. Okay, very good, everyone. So I hope all of you understood this. Yes or no? I hope all of you understood this. Okay, now think about it. Think about it. So out of this three, which is acting as a source? Tell me, which is acting as a source of electrons? Which side is acting as a source of electrons? Leftmost. Very good, very good. So this is acting as a source. This is acting as a source, right? Which is acting as a drain, right? Which is acting as a drain of electron. Drain means from where electron is leaving out. Right side. Very good. Drain is right side. No, drain is right. Most of the electron is going out from this side. Okay. Now, what is the role of this middle one? The role of this middle one is to maintain some balance, right? To maintain some balance. Yes or no, right? So this will behave as a gate. Okay, gate, because it will allow only few electrons to pass through it, right? Okay, it will allow only few electrons to pass through it, because just think about it now, think about it, right? It is p-type, it cannot have more electrons. Okay, so suppose it have only 5 holes and 5 electrons, right? So I can say that if it is having only 5 holes and 5 electrons, then due to this potential difference, only 5 electrons can pass through this gate, right? Only 5 electrons can pass through this gate. Yes or no? Right? Now suppose we have 100 electrons over here, 100 free electrons over here. Because of this forward biasing, 100 electrons will jump from here to here, right? So it will be having 100 electrons here, okay? Again, we have a potential difference now, Manoj. So obviously this electron will go outside, okay? This electron will go outside, okay? Now out of that 500 electrons, only 5 electrons will go outside, okay? What about 95 electrons? 95 electrons will find their way into this type, this N junction. Yes or no? Tell me. Right? Okay. Right? Okay. So I hope all of you understood the basic structure, basic construction and working of your PN junction. Yes or no? Right? Both the PN junctions. Okay. Very good. So this is the general term I used here. Okay. This is just the term which is used, Harsha. Okay. This is the general term. Okay. For you, it is not called as gate, right? For you, it is called as base. Okay, so this nomenclature is because of the working, okay, because of the working, but depending on the first structure of this transistor. When you talk about the first structure of transistor, I hope all of you watched the video. There it was mentioned why it was like this, okay. But when you talk about the first structure of transistor, okay, according to that, this P type, okay, was as a base. It was acting as a base, so it is called as base. Okay, that is conventional name, base. Now since this side is emitting electron, right, it is giving electron, it is called as emitter. Okay, and since this is collecting electron, it is called as collector. Got it? Right? So source, gate and drain is a nomenclature which can be used for all the transistors, okay, right? So this is depending on the function, and this is depending on the basic convention. Okay, everyone, tell me, okay, right? Think about it. Okay, so here I talked about, okay, this side, emitter, right? Emitter should be highly doped. Okay, this base should be very lightly doped and very thin. What about this? What about this N type? Think about it. What about this N type? It should be highly doped, lightly doped, moderately doped. Okay, lightly doped. Why is it so? Just think about it. We know that if anything is highly doped, right, the depletion region will be less. Yes or no? Right? The depletion region will be less. Okay. Now, if depletion region is less, the electron will move like really fast. Okay. It will just, right, it will just shift from P type to N type. Okay. And this process, this movement, right, provide like release energy. Okay. This movement release energy. Okay. Got it? Right? And if this process happens rapidly, okay, without any constraint, so it will produce very high heat. Okay, it will produce very high heat, and this whole junction can collapse. I hope all of you remember, right? Breakdown voltage, right? So that's why we have to maintain, right, this reverse bias junction, okay, such a way that the depletion region is thick as compared to this junction, okay. And in order to do so, we should have lightly doped, right, or moderately doped N side on this collector side, okay, right? Okay, so I will show you. So here I'm taking NPN. In the same way you can take PNP also. Yes or no? Tell me. In the same way you can take PNP also. Okay, right? The only difference would be, okay, instead of electron, right? Instead of electron, you can just see the movement of holes, even though it's electrons only, but we will talk about the movement of holes. Okay, got it, right? Okay, let's see. So this was the basic construction that we saw for NPN. This is NPN, right? Emitter, base, collector. and PNP, again, it will be emitter base collector. Okay, right? Now, this is the constructional diagram. What about the diagram that we will be using? Whenever we use, right? Whenever we use the symbol of this transistor, we will use this, right? Okay, why? Again, there's a story behind why we use this symbol. Okay, because when you talk about the first transistor which was made, okay, it was like this. It was like this. The first transistor that was made was something like this only. Okay, right? It was base and emitter and collector was like this. Okay, I'll just show you the video someday. Not video, I'll just send you the pic. Okay, now that has made the convention. That's why it is shown like this. Now, it might be confusing for you to know which transistor is NPN and which transistor is PNP, right? That is very easy. Just think about this junction. Just think about this junction. We know that current will always flow. Current will always flow from P to N, yes or no? Because electron will always flow from N to P, right? Now just think about this. I can say that, okay, current will always flow from this side. If it is emitter, right, base to emitter, as simple as that. Current will always flow from base to emitter, as simple as that. Current will always flow from base to emitter in case of NPN. Okay, right? Now, if you remember this, you might get confused. Okay, you might get confused. So that's why I told you, you should always think it will flow from P to N instead of remembering base to emitter, because many people do that and it is confusing, right? Because when you talk about PNP, if you see PNP, it is emitter to base, right? See this. But if you remember this convention, right, from P to N, always from P to N, see P to N, right? Here, P to N. Got it? Right? So base, if you talk about NPN, base is P, right? And this is NN. Okay. So it is either this or this, doesn't matter. If you make this, then this will become your emitter. If you are showing this direction, then this will become your emitter. Yes or no? Tell me guys, yes or no? Right? So always remember P to N. Okay. Now when you talk about N, so either this is P and this is P. So if you draw like this will become your emitter, right? And if you draw like this will become your emitter, right? Because obviously any one of the two sides can be emitter, right? This circuital representation that we will be using for our numericals. Okay, and this is the construction based on the junctions. I hope all of you understood these two. Tell me, I hope all of you understood these two. Raise your hand if you understood these two. Raise your hand. Okay, very good, right? Now, let's talk about the voltage. Yes, Harsha, obviously. Now, according to doping only, the current will flow. Na? Think about it, right? Current will flow from highly doped to less doped, right? Highly doped p-type to less doped n-type. Okay, so I'm just talking about this structure, right? For example, if instead of this, if I would have given like this, right? Suppose if I would have given like this, then which of the two sides would be emitter? Tell me. This side would have been emitter now, right? It is just the representation I'm talking about. Okay, got it, right? Okay, very good. Okay, now if you see this, if you see the structure, right? If you see the structure, I'm talking about NPN only because you can just take the analogous for PNP, because I'll be talking about NPN most of the time. You can just take the analogous for PNP. It will be same. Now, in NPN, we observe that if I'm having 100 electrons, right? If I'm having 100 electrons in E, so 5 electrons will move to B, 5 electrons, yes or no, right? Yes. Okay. and 95 electrons will move to collector. Okay, okay, very good everyone, right? In the same way, here, right? I can say that if I'm having 100 holes in P, 100 holes in P, right? 5 holes, okay, right? Tell me, 5 holes will go here and then 95 holes will go here, right? Just think about the holes, right? Okay, okay, right. So now let's talk about, yes, let's talk about the parameters. I hope all of you understood the construction working principle. Tell me, guys. Okay, very good. So see, this is your structural representation. Okay, right? This is when you talk about these two junctions. So when you talk about PNP, this PN junction is forward biased and this NP junction is reverse biased. Okay, when you talk about NPN, this junction is forward biased, right? And this junction is reverse biased. Okay, right? Now when we talk about this circuital representation, okay, so current will flow from P to N. Remember, always P to N, P to N, right? That's the thing. And P to N, right? And it will always be the direction of current, right? Which will be shown, will be between base and emitter. Okay, right, everyone? Okay, so I hope all of you understood this. Yes, very good, everyone, right? Very good. Okay, just give me 1 minute. Okay, right? So yeah, so we studied what's collector, right? Yes or no? And we studied that when we talk about this transistor, we have two junctions. Okay, two junctions. One is emitter-based junction and one is collector-based junction. So emitter-based junction is forward biased, right? And collector-based junction is reverse biased, right? Okay. Yes, very good. Okay. Now think about it. Think about it. Now we will talk about the working of this transistor. So as we have discussed, this transistor can work as, right, either switch or amplifier, yes or no, right? Yes or no. Now we have to know, okay, when it is working as switch and when, okay, if you remember, I talked about the junctions, the biasing of these junctions, okay, right? That if this base is 0.7, then this junction, I'm talking about, it is not always 0.7, I'm considering silicon. Okay, that's why for silicon, it is 0.7. I hope all of you remember from the last class, right? Okay, and suppose I'm considering this as 5 volt or 6 volt, doesn't matter. And this is at zero potential, okay, right? Now just imagine if I'm having a voltage, which is less than 0.7 here, right? V base or voltage as base. It is V collector and it is V emitter. Okay. Suppose V base is less than 0.7. Suppose. Then what do you think? What will happen? Tell me. What do you think? What will happen? It's intuitive, right? Okay, just think about it. What will happen? Ask yourself. Vishnu, right? First of all, it is if it is less than 0.7, it is not forward biased. Yes or no? Tell me. If you remember PN junction, right? In order to current flow, in order for electrons to flow from N to P, okay, right? The potential should be more than 0.7. Yes or no? Tell me. This is what we have already studied, right? Right? If it is less than 0.7, then it cannot overcome the barrier potential because 0.7 is a barrier potential, right? So if the voltage at base is less than 0.7, I can say that, okay, at this stage, right, even though it is forward biased, but it is not having sufficient voltage to cross the barrier potential, right? Yes or no? Right? Or their base current should be zero. Agree? Tell me, agree? Because electron is not moving from N to P side. Anyone have any issue in this? Anyone have any issue in this? Think about it. Think about it, guys. Yes, current won't flow now because electron, see what is current? It is basically, right, conventionally, it will always be the opposite direction of electron flow, right? Basically, it is the flow of electron which gives rise to current. If electron is not flowing, if electron is also not flowing from N side to P side, how can we have current? Think about it now, right? Got it? So I can say that electrons will not flow, so current will not flow. Now, if IB is zero, right? Can you think that can electron move from P type to N type? Because electron doesn't even reach this P type from N type, this N type, from emitter to base. Electron is not even moving from this emitter to base. How can they move from base to collector, right? So this current, which will be in collector. So this is your IC, collector current. This is called your IB, which is base current, and this is called your IE, right, which is your emitter current. Okay, right? Sorry, it will be in this direction, no? Right? It will be in this direction and it will be in this direction because electron is moving in this direction, right? Tell me yes or no. So collector current will also be zero. Yes or no, guys? Tell me. Yes or no? This is the case when this potential is less than 0.7. Okay? Okay, very good. So I can say that, let's talk about this. If this junction, we have junction A. So this is junction 1, and this is junction 2, which is collector base junction. Okay, doesn't matter if it's PNP or NPN. Now, if this is forward biased and this is reverse biased, reverse biased, it will work. Yes or no? It will work. Agree? Right? It will work as an amplifier, right? So this is called as active region. It is called as active region. Okay, right, everyone? Okay. Now, again, if it is reverse biased, it is forward biased, right? It will work, but it won't be that effective. The amplification will not be that effective because of the doping. Okay, right? If the doping is almost same, then you can say that it is same, right? But since the doping will not be same, okay, right? This region will not be as effective as this one. But again, this is just for theory, right? This is not practical case. Okay. Now, what about if this is reverse biased and this is also reverse biased, right? What is this case? This is the case when VB is less than 0.7. Yes or no? Tell me, yes or no? Right? Right, everyone? Okay. Now both junctions reverse biased. If both junctions reverse biased, right? It will not flow. The current will not flow, right? It is called as cutoff region. It is called as cutoff region. Okay. Cutoff means no current is flowing from from collector to emitter or base to emitter. No electron is flowing from N to P and then P to N. Okay, everyone, got it? Right? Tell me, right? Okay. Now, the last case is when both the junctions are forward biased. This is also forward biased. Okay. Now, this is called a saturation region. I'll explain you how this is saturation region when we talk about the common emitter circuit. Okay, when we talk about whole process, when we talk about what is emitter current, what is collector current, then you will get to know why this is called a saturation. Okay, right, everyone? Right? Now, what is meaning of saturation? First of all, tell me, what is meaning of saturation? Maximum, right? Okay, maximum means whatever you do, it won't increase from that. Okay, right? That is meaning of saturation. So we'll discuss the saturation. Okay, we will discuss all the three, by the way. Okay, now we talked about the doping. I already said that emitter is medium size, high doped, base is very small, thin, very low doping, collector largest in size, right, and medium doping. Got it? Right? It is true for both NPN and PNP. Okay, right? And I have already told you, okay, the collector is large than the emitter because it should accommodate for the huge exchange of energy, right? When the large amount of electron is moving from P to N. Okay, because it is reverse biased, no? It is reverse biased, right? Okay, right. So I hope all of you understood the working of transistor. Tell me. I hope all of you understood the working of PNP transistor, sorry, NPN transistor. Anyone have any issue with the working of NPN transistor? And think about it, right? PNP and NPN will be almost same, right? It's just that instead of moving electron, just move your holes, right? Okay, relationship between collector current. What is the relationship between collector current IC, emitter current and base current? Tell me. Think about it. What will be the direction of electron? When you talk about electron is moving from this side to this side, right? Electron is moving from emitter to, tell me, base, emitter to base, and then base to collector, right? So the current will flow from collector to base. Tell me, yes or no? Kirchhoff junction law. So the current will be in opposite direction of the direction of flow of electron. So this and this. So can I say that? Okay, it will be IE is equal to IC plus IB. Yes or no? Tell me. Yes or no? IE is equal to IC plus IB, Kirchhoff's junction law. Okay, right? Okay, very good. Very good, everyone. And if you see the structure, which junction is common? Tell me, which junction is common here? Which junction is common with all the other junctions? Base, emitter, collector, which junction? Base, right? Because see, base is connected with both emitter and collector, and right? Got it? So this configuration is called as common base configuration. Common base, right? This is called as common base. Common base. Okay. Right, everyone? Right? In our syllabus, we have to study common emitter. Okay, so we'll be focused on common emitter only. Okay, but we will see the structure of all the three: common base, common emitter, common collector. It is quite easy, right? You just have to see the junction. Okay, right? You just have to see the junction. If the junction is common in collector, then it is common collector. If the junction is common in base, then it is common base. If the junction will be common for emitter, then it will be common emitter. Okay, right, everyone? Right? Okay, so I can say that the number of electron which is moving from P to N, right? The number of electron which is moving from P to N, right? Also depends on the number of electron which is going from this base going to base. Yes or no? Tell me. Yes or no? Right? Because just think about it. Just think about this, right? If we need more electron, if we need more electron to go from, right, more electron, right? Think about it. Okay, if we need more electron, okay, to move from this base, right, to the circuit, okay, it means there are more electron moving from this side to this side and more electron moving from this side to this side. Yes or no? Think about it. Yes or no? Means if I can say that, if I'm having 100 electrons and 5 electrons is moving, right, in the circuit, 5 electrons is moving in the circuit and 95 electrons are moving here, right? But if instead of 5, if I'm getting 50 electrons, what does that mean? What does that mean? It means that here it should be 950 electrons now. Tell me. It should be 950 electrons and this should be 1000 electrons. Think about it. Yes or no? Yes or no? Because this ratio is always constant, right? Because it is lightly doped, Manoj, right? How can it suddenly changes its doping? Think about it, na, right? Think about it. If a room have only 10 seats, how can suddenly they have 50 seats, right? Got it? Right? So this ratio, okay, in which, right, this ratio. So I can say that if IB will be more, if IB will be more, okay, if IB will be more, IC will be more. Yes or no? Tell me. Yes or no? Think about it. And IB, this current, this base current will be very, very less than, it should be very, very less than this current, right? Okay. Yes or no? Tell me, guys. Yes or no? So there's a relationship between IB and IC, which is this: IB is equal to beta time IC, beta time IC. Okay, right? Sorry. My bad. This I just made a mistake. Okay, it's not like that. Hello, can you hear me? Right? So yeah, So basically IB will be very less than IC. Okay, and beta is a factor which is very greater than, right? It is basically greater factor, right? So I can say that IB is equal to, or IC by beta. Okay, or IC is equal to beta IB, right? This was opposite. Okay, got it? Okay, so anyways, I hope all of you understood this relationship between IC, IE, IB. Okay, okay, and the working principle and the characteristics. Beta is called as current gain. Okay, beta is called as current gain. Okay, Prashant, right? Because current is changing now. IB is normally termed as input current. Okay, right? IB is generally termed as input current, and IC your current gain. Now let's see. Yes, Manoj, you can apply loop law. Okay, right? But I don't think that in your, like, in class 12th you need to use loop law. Okay, but if anyone, like in college, you have to study this. Doesn't matter which branch you take. If you take circuital branches, you have to study this. Then you can get a complex circuits, and you have to use KVL, KCL, right? So if you see this, this is the construction and working of PNP transistor, right, everyone? Just see this. This is the construction of PNP transistor, and everything is same, right? Everything is same. Instead of electron, we are having holes. Yes or no? Instead of electrons, we are having holes, right? Okay, got it? Yes or no? So this is IE, by the way, this is IE. So here also IE is IB plus IC, right? So it doesn't matter if you're talking about PNP or NPN, IE is always IB plus IC. Okay, right, everyone? Okay, so we completed the first topic, which was construction and working principle, constructions and working principle. Okay, now when we talk about the configuration, I told you that depending on the common junction, we have different type of configuration. Now think about it, this, in this, which junction is common? Tell me, guys, in this circuit, which junction is common? Tell me, which junction is common to both or the two other junctions? Tell me, everyone, tell me, what do you think? No, na. How can it, how it is base? This is, see, this is your collector, this is your emitter, and this is your base, right? This is your base. So which junction is common? Tell me. See, this collector is joined over here. This base is also joined over here. So this emitter is common, na? Yes or no? Right? Yes or no? So this is called as common emitter configuration, right? So we have to study in our syllabus, we have to study common emitter characteristics only. Okay, right? Now I'll show you the all other, yes, I'll show you all other characteristics also, right? So we have three configuration: common base configuration, common emitter configuration, common collector configuration. Okay, now when we talk about common base configuration, right, it will have high voltage gain but no current gain. Okay, common emitter configuration is the best. That's why we will be studying about this. It is the best because it is having both current gain and voltage gain, right? Okay, and common collector will have current gain but no voltage gain. So we won't be studying about this and this in our syllabus. Okay, but we should be able to identify what is the difference between these three. Okay, now when we talk about common base, so we have already seen that base will be common. Yes or no? See this, base is common over here, right? Okay, now what's the meaning of base is common? It means now collector is always this output. Okay, collector side is always output. Okay, got it, right? And base side or emitter side may be input. Okay, current gain means how many times current is increasing, output current is increasing, right, with respect to input current. Okay, and voltage gain mean how many times voltage is increasing. We will see that. Okay, for example, we saw this now, IB, right? So, sorry, IC by IB is equal to beta, yes or no, right? Right? So this is your current gain. This is your current gain. Okay. Now in the same way, right? Second thing is common emitter. So if you see this, here the emitter is common, the same structure that we saw now, right? Now, if you see this, right? Which is your input side? Tell me, which is your input side? Think about it. Which is your input side? You can get the answers. You can get all the answers. Which is your input side? Base is your input side. Yes or no? Base is your input side, right? And we know that this base current is very less. Base current and base voltage is very less. Yes or no? It is very less, right? And we want amplification, okay? And think about it. If base voltage and base current is input, right? Output is always collector. Output will always be collector, okay? So here I can say that here in case of common emitter as well as in case of common base, output is collector. It is just the representation, Prashant. It is just the representation. Okay, got it. It is just the circuital representation. Before this image, this one. So see this now, both are same, right? See this, both are same, right? It's just the connection which is different. Otherwise, when you talk about this transistor itself is same now. Collector, emitter, base. Got it? Tell me. It's just rotated 90 degree. Okay. It's just rotated 90 degree, nothing else. Okay. Okay. Now these are the parameters that you should remember. Think about this. This is your, remember this structure, right? Now, obviously, we cannot have a circuit without resistance, right? Because then we will have infinite current, which is not desirable. Okay, so the resistance, right? Resistance between your collector and this common emitter, right? Okay, this is called your load resistance. This is called your load resistance. Okay, got it? And what is your output? This V naught. This is called as V naught, right? This potential is called as V naught. Okay, got it, right? And this potential between this and this emitter, it's called as VCE. This is also called as VCC. Okay, now potential here, right? Between B and E, this potential, this point is VBE. Remember this. I will be using this, and this VBE for silicon, it is fixed as 0.7. Okay, got it? Tell me, got it? Okay, now it is said that this is VBE, but this is not VBE, right? This is just VB, because there should be some current, some voltage which will be dropped in this resistance, yes or no? Tell me, yes or no, right? Okay, it is equal to VBE when there's no current in the circuit, right? So that's why this is just VB. The VBE is between this and this. Okay, this is what you have to remember. Now, when you talk about, when you solve some problems, then you will get the clarity, don't worry. Okay, now when you talk about common collectors, so common collectors like this, Okay, in this case, the load will be from emitter. Okay, don't worry, we won't be studying this. Okay, if you see right here, collector, right? Okay, okay. So see, this is the relationship that we have already studied. Yes or no? Tell me. That emitter current is always equal to base current plus collector current, right? And the ratio between collector current to base current is called as beta. Okay, and the ratio between collector current and emitter current is called as alpha. Now, don't you think, huh? Which direction of IB is opposite to IC? In which case, see, will be talking about common collector only, right? So where it is opposite? In common collector, it is same, na? Sorry, see, right? Common emitter case, it is same, right? This is a mistake, right? This is a mistake. Don't worry. See, collector base will give emitter. It's same. See, this is also going this side and this is also going this side, right? In common emitter. When you talk about common base, think about it, right? Current direction. This is also going this side and some amount is going at this side. Okay, so it's not same, it's not different, right? It is same direction. Yes or no, Prashant? Tell me. IE is equal to IB plus IC holds true for all the cases, be it common base, common emitter, common collector, right? It will hold true for all the cases. Okay, got it? Everyone got this? Step by step, right? Step by step. Okay. So I hope all of you understood the configuration. Tell me, all of you understood the configuration, right? So we covered this and this and this. Okay, right? I hope all of you understood what is the working principle of bipolar junction transistor, right? Of PNP, NPN, then different configuration and different parameters. Okay, right? Okay. Now let's talk about the input and output characteristics. Here we are talking about only common emitter, by the way, right? We'll be studying common emitter. Okay. Okay, everyone? Tell me. Fine. We will be talking only common emitter, right? Now see this. Our syllabus is usually common emitter. Now, what do you think here? What do you think here? What is V input? Tell me. What is V input? Or what is voltage drop between these two? Tell me. What is IB? What is IB? Tell me, everyone. What is IB? This is VBE. This is VBE, which is equal to 0.7, right? Think about it. Now, use your Kirchhoff's law. As simple as that, right? VB is equal to what? This is a higher potential. This is a lower potential, right? So I can say that. Wait, I can say that VIN minus VBE, right? This is the potential drop between these 2 points. Yes or no? Yes or no? Step by step, right? This is equal to IB into RIN. Yes or no? Right? Anyone have any issue in this? Anyone have any issue in this? Tell me. Clear? Now, when you talk about this circuit, output circuit, let's talk about output circuit. Now, instead of VCE, I'll call it as VC, just VC, right? Okay, or supply voltage, VS, supply voltage. Okay, this is your supply voltage, and this is your suppose it is VC, right? Because this is point now VCE, right? This is VCE. Okay, so what do you think? VS will be greater than VC or VS will be less than VC? Tell me. Supply voltage will be greater than, okay, this is VC, not VE. Okay, supply voltage, VC. Okay, supply voltage should be greater than or should be less than? Very good, Prashant. right? Supply voltage is always greater than VC, right everyone? Okay. Okay. So I can say that for this, it is Vs minus Vc, okay, Vs minus Vc, which is your output voltage, is equal to IC into RL. Agree? Yes or no? Agree? Okay. Now think about it. Now think about, yes, now think about the characteristics. Now, what do you mean by input characteristics? Input characteristics means variation of I with respect to voltage. Yes or no? Input characteristics means variation of input current with respect to input voltage, right? And output characteristic means variation of IC with respect to V, output voltage. Yes or no? Yes or no? Tell me. So variation of, right? Variation of IB, right? With respect to input voltage is your input characteristic. Agree everyone? Agree? And variation of IC with respect to VC is your output characteristics. Yes or no? Tell me guys, yes or no? Step by step, right? I'm just talking about IV characteristic, right? For input circuit, it is input characteristic. For output circuit, it is output characteristic. Now, let's see, right? So I hope all of you understood till this point. I hope all of you understood till this point. Yes or no? Anyone have any doubt till this point? Right? I just wrote the simple circuit equations. Okay, just have a look. Okay, very good. Right? So it's clear for most of you. Very good, everyone. Okay, very good. Now let's see this. Now, when you talk about input characteristic, right? VC. Okay, because VC will change, na Harsha. Supply voltage will be fixed, right? Supply voltage will not change, na, right? Voltage will change, yes or no? Think about it, na, right? Vs is the battery, Vs is the supply voltage, right? It is not going to change. Okay, think like this, think intuitively, right? Now, don't you think that this input characteristic is just your forward biased characteristic? Yes or no? Tell me. This is just same as forward biased diode characteristic? Yes? Tell me. As the input current increases, right, after some value, after 0.7, right, the current will start flowing same as forward biased. Agree, everyone? Agree? Right? And the base current will be very small. The base current will be very small. Okay? Okay, very good. So I hope all of you understood about input characteristic. Now let's see output characteristic. Okay. Now what do you think? What would be the output characteristic? How it will be? Think about it. Everyone try to draw output characteristic by your own. Okay, try to draw it. Okay, try to draw it. Try to draw it, everyone. Output characteristic. Does it look like this? This is the actual graph. Okay, think about it. So as I said, right, this is between IC and VC, or basically VCB. Okay, right? Right, everyone? Now, if you want to know how this, why this, just think about it. Vs minus Vc is equal to IC into RL. Okay, agree? Right? Now, we know that VC cannot be more than Vs. Yes or no? Tell me. Right? Collector voltage cannot be more than supply voltage, na? Yes or no? Cannot be more than supply voltage? Think about it. Can it be more than supply voltage? Tell me. Can collector voltage be more than supply voltage? No, right? It cannot be more than supply voltage. Okay, right? Yes. So think about it. This cannot be more than supply voltage. Now think about it, right? When IC will be maximum, when collector voltage is almost equal to this, IC will be minimum, right? Or when VC is almost zero, IC will be maximum. Yes or no? Yes or no? Tell me, guys. Okay, so can I say that as IC increases, VC decreases? Think about it. As IC increases, VC decreases. Right? Let's see this structure. Okay, let's see this. Okay, everyone see this? Yeah, sorry. Yeah, sorry. Thank you, Harsha. So yeah, I was saying that if IB is zero, IC will also be zero, and as IB increase, IC will also increase. Yes. Okay. But the question here is, will IB keep on increasing? Will IB keep on increasing? The answer is no, right? Because at one point it will saturate. Okay, why is it so? Now, if you see the structure, right? If you see the circuital structure, okay, I'll just draw one. Over here, okay? Right? So this is your input RIN, and this is your, suppose, RL, right? And this is your, suppose, we supply, and this is VC, okay? And this is your, again, right? Now think about it, IC. What is the voltage drop? Suppose this is your 5 volt. Suppose this is your 5 volt, okay? 5 volt, okay? Now, and RL is, suppose, I'll just give any one value. RL value I gave you, like, suppose it is 2 milli ohm, 2 milli ohm, right? Sorry, not milli, 2 kilo ohm, right? 2 kilo ohm. Suppose it is 2 kilo ohm. Okay, everyone, right? Tell me. Okay, so we have supply voltage as 5 volt, okay, and this RL, load resistance, as 2 kilo ohm. Now suppose you keep on increasing the current IC. Suppose you keep on increasing the current IC. Okay, what will happen? Tell me, what will happen? Think about it. Suppose your IC, right? Suppose your IC is around 2 milliampere, right? Okay, 2 milliampere. So what is the voltage difference here? What is the voltage difference between Vs and Vc? Tell me. If IC is 2 milliampere, what will be the potential drop between Vs and Vc? Tell me everyone. 4 volt, right? Means potential here should be 1 volt, right? Okay, this is case 1. Case 1. Case 1, right? It is still forward biased. It is still forward biased. It will still continue conducting the current, yes or no, right? Because this should be forward biased, right? Now suppose IC increased to 2.5 milliampere, 2.5 milliampere, case 2. This is case 1, this is case 2. Now tell me, now what it will be IC? What will be the value of IC? Tell me. Because this current is 2.5, the voltage drop between this should be 5. But if it is 5 and voltage drop is also 5, then this should be 0. Tell me, this should be 0. Are you getting my point? This should be 0 volt. Yes? Right? I hope all of you relate when I said VC should be 0 for I to be maximum. And I hope all of you know now why it is 0. Now, do you think that can we have 3 milliampere? Can we have 3 milliampere? Tell me. Can we have IC is equal to 3 milliampere? No. Why not? Because if we have 3 milliampere, then the voltage here, voltage of C, right, should be how much? It should be minus 1 volt, right? Minus 1 volt. Now, can this be reverse biased? Can this be reverse biased now? No, right? It will be forward biased now, because we know that potential drop here is 0.7, right? This will be more than this. Okay, so this will be forward biased. So not possible, right? Okay, right? For working in active region, right? So maximum current is 2.5 only. Yes or no? Tell me, yes or no? So IC cannot be more than 2.5. Agree everyone? In this case, I'm just talking about this case. Yes or no? For a fixed IB, obviously, for a fixed IB. Okay, got it? So that's why whenever, right, that's why whenever you try to increase VCE, okay, for fixed IB, there will be a one fixed IC, right, at which it will stop increasing. Okay, so it will increase like this, but after this it will stop increasing. Got it, everyone? So this is your output characteristic. I hope all of you understood output characteristic. Tell me, all of you understood output characteristic? Yes or no? Yes or no, guys? Tell me. Tell me, everyone. Okay, right? Now, yes. So let's see what will happen to voltage. This was about current, right? So, yeah. So this is your output characteristic. If you can see, this is your output characteristic, right? Okay. Now, if you observe this, then this characteristics is divided into 3 regions, right? It is divided into 3 regions. Okay. Now, one is this region in which IC is increasing linearly. Okay, right? Okay, got it? So we have this first region, the second region, and this third region. Okay. Now this first region where current is maximum, IC is max, right? And this second region where IC is almost 0, right? Don't you think that these two region, right? These two region is acting as a switch? Yes or no? Tell me. It means I is maximum means switch on, right? And IC is 0, which is switch off. Agree? Tell me, agree? So if I ask you in which region your transistor act as a switch, tell me in which region transistor will act as a switch. This is called as cutoff region. This is called as cutoff region where current is 0. It is called as cutoff region, right? So I can say that the transistor will work as a switch, will act as a switch in cutoff as well as saturation region, right? So I hope all of you understood what is cutoff region, what is saturation region. Tell me yes or no. Saturation region is a region where IC is maximum, okay, and cutoff region is the region where IC is minimum, okay, right? Right, everyone? Right? Now, this is about current. If you talk about voltage profile, VC, okay, so don't you think VC will be something like this? It is power, okay, I'm not talking about power, I'm talking about VC. VCB will be something like this, right? For some point it will be maximum, then it will start decreasing, right? And it will be 0 at some point. This is base current, Prashant, as I told you, right? These are the different current characteristics for different bases, right? Base current. This is for first base current, right? Second base current, third base current. Okay. Because you have only one line, na? You have only one line for one base current. Got it? This is just a general representation for many base currents, right? Because if base current will be more, then your IC will be more, saturation IC will be more, saturation current will be more, okay? And this is a voltage VC. I hope all of you can relate now, right? As current will increase, okay, VC will decrease. So this region for VC, this region is your saturation. Sorry, this region is cutoff because voltage across this will be maximum, and this region will be saturation because this voltage is 0, right? So I hope all of you know that when voltage across switch is maximum, it is off. Yes or no? Tell me. When voltage across switch is maximum, it is off. Agree, everyone? And when voltage across switch is 0, it is on. Okay. Okay. So I hope all of you understood this. Input and output characteristic, right? Voltage one is not in your syllabus. But I just gave you the idea because you can just relate with the formula, right? Okay, as IC will increase, VC will decrease. Okay, VC will decrease. Okay. Okay. So I hope all of you understood these things. Tell me, guys, I hope all of you understood these things. Okay, so we have covered till this. Okay. Okay, so we will be having one more class, okay, from 5:30. Okay, so from 5:30, I will be continuing this. Right? Plus, after everything is over, right? I have sent some doubts. I will cover those doubts also. Okay, right? But we'll be completing this exercise for today. Okay, everyone. Okay, so 5:30 we'll be having another extra class of chemistry till it get over. Okay, till it get over. Yeah, Vishnu, take attendance and post in the group itself. Okay, so I hope all of you understood till this point. Tell me, all of you understood till this point? Yeah, we will start at 5:30, 5:40. Okay, or I'll just ask ma'am to leave a few minutes early. Okay. Or I'll leave logic gates for today. Okay, I'll leave logic gates for today. I won't be covering logic gates, but application, right? So it is like 30 minutes to 45 minutes topic. Okay, So I hope we will be able to cover till 6:15, 6:30. Okay. Okay, everyone. Thank you. You have chemistry class? Yeah, we have class tomorrow. Okay. Bye, everyone.